right. Hello, hello. I believe we are now live. Hello, everyone. Good afternoon, good evening, wherever you are in the world. Welcome to our webinar today. I'm super excited to be joined by Adrian Messer for today's presentation. Backing up for a second, my name is Heather Grant. I am one of the community admins here at the maintenance community by Upkeep. Thank you for joining. If you are not already a member of the maintenance community Slack group, we would love to have you join us there as well. We will add a link on how to sign up in the chat in just a moment. Today, as I mentioned, I have Adrian Messer joining me for our presentation. Adrian is the Director of U.S. Operations for UE Systems, and he supports current users of ultrasound technology to improve overall plant and facility reliability. He's passionate about educating others on the value and the benefits of integrating ultrasound into their existing programs and procedures. So Adrian, thank you so much for being here.
Yeah, appreciate that, Heather, and it's great to be back here with the Upkeep community, and appreciate you all taking time out of your day to listen to the presentation, and hopefully you will have, by the end of the hour, you will have walked away having learned something about the technology, and hopefully something that you can implement back at your facility. That's kind of what my goal is for today. So, we've got 5 ways to reduce energy waste with ultrasound, and I hate to say that this is a more basic presentation, but certainly if you're on the call today and you're not familiar with ultrasound, energy conservation is one of the easiest applications that you can take an instrument right out of the box, and you can have a pretty quick return on investment. And we're going to talk about each one of those ways and how we can report and document our findings. And that's really critical with not just energy conservation initiative, but really with any maintenance and reliability initiative. And I always say, anytime I'm in front of a group of people talking about, ultrasound and maintenance and reliability, in all of my visits and interactions with people in the industry, if there's one thing that I see that maintenance and reliability professionals can do better, is with reporting and documentation, really just showcasing exactly what it is that you're doing. And anytime we can put a dollar amount to that, somebody, they may not understand, hey, we went out and we found 40 air leaks today, but they may understand, hey, we found $10,000 in air leak costs today, or air leak, waste today. So anytime you can put a dollar amount to that, that's only going to help to create buy-in and awareness for exactly what it is maintenance and reliability can do, and really helps to show maintenance and reliability, really as adding value as opposed to just being a cost center. And unfortunately, in some plants, facilities that I go to, maintenance and reliability kind of has that association with it, that it's nothing but a cost center, when really we need to be showing that we're adding value back to the organization. So certainly, if you have questions, we should have some time at the end to get to some questions. And I think you saw my email address here on the first slide. So anything that we don't get to today, or after you watch this, if you think you really wish you would have asked a certain question, feel free to shoot that to me in an email. I'll be glad to field those. Really, when we look at, energy conservation and, energy initiatives in our plants, an energy efficient plant can be directly linked to the reliability of a plant. When I'm going out to visit a plant, I can usually tell not only what the culture is going to be like, but kind of what the overall reliability of the plant is, and how energy efficient that plant is. A lot of times from the time I pull into the parking lot, but certainly by the time I walk into the front door to the lobby, I can usually kind of get an idea as to what it's going to be like behind the doors. But we think about the overall reliability of a plant. A lot of those aspects can be directly related to how energy efficient that plant is. So they are interlinked together. And, we think about common sense. Common sense plays a major role in being responsible and smart with our energy usage. Unfortunately, what I see is, a lot of times when I go into these plants, the people that I'm meeting with, they have been in this plant for, decades, sometimes, 15, 20 years. And, a lot of times we just get used to, oh, that's just the way it's always been, or we just get used to, that's just the way things are. But, it doesn't have to be like that. So I encourage people to if they've been in their plant for a long time, just go out and, form a team of people, and similar to what you would do with like a Kaizen event, to where we're going to take a machine and we're going to walk this machine. We're going to think about, how we can make it more efficient, more reliable. How can we improve this process? But, form an energy team to do nothing but go out into the plant and walk the areas of the plant and do nothing but look for areas where we can be more energy efficient. And again, you'd be surprised at what you may find, especially, if you've been in a plant for a long time, and, the mentality is, oh, that's just the way things are, or that's just the way things have always been. And then, I've already talked about reporting and documentation. So for many of these, for at least 3 of the 5 applications, or the ways we can reduce energy waste, we're going to show you easy to generate reporting and documentation items that you can create and use based off of your ultrasound data and your ultrasound findings. So again, that's going to be critical in helping to not only show the value of what ultrasound can do in terms of helping to reduce energy waste, but again, helping to create and show that overall value that maintenance and reliability brings to the organization. So first of all, as just kind of an introduction to the technology, ultrasound is another one of those extension of a person's senses. So just like an infrared camera sees what you can't see, just like an accelerometer feels what you can't feel, ultrasound hears what you can't hear. And we really focus on these 3 core application groups. So we have leak detection. So that's going to be compressed air or compressed gas leak detection. Steam traps. So if you're in a facility that has steam, so maybe you're using steam for as part of the process, or maybe you're using steam for heating, you can have failed steam traps, and ultrasound can detect those traps that may be either leaking by or failed open, to where they're just constantly blowing live steam across the seat of the trap. And valve leak detection. So using ultrasound and contact ultrasound specifically, we're able to listen to valves to make sure that those valves are, open, or if a valve is supposed to be closed, to make sure that there's no leak by present. We can do that with ultrasound. And electrical inspection, to where we're using airborne ultrasound to listen for common electrical faults like corona, tracking, and arcing. One of the main factors that's really driving that application is it's a safety initiative, because we don't have to open up panels or cabinets to scan inside with an ultrasound instrument like we would with a traditional infrared camera. So what a lot of people are doing is, before they ever open anything up to do an infrared scan or to do any kind of maintenance or inspections, they're listening first with ultrasound to make sure that they don't hear corona, tracking, or arcing taking place, because that sound will exit out wherever there's an opening. So we can just simply scan the seal of the door, louvers, vent openings, and we're going to be forewarned about any potential problems taking place inside of that cabinet before we open it up. So in a sense, we're reducing the risk or the chance of an arc flash occurrence. And then I would say where the majority of our users are using ultrasound for, and that's going to be equipment reliability and condition monitoring, to where really they're complementing vibration analysis by using ultrasound as kind of a standalone CBM tool to go out and routinely check the health of bearings and rotating equipment to make sure that there are no signs of any impending failure. And then also condition-based bearing lubrication, where we're more precisely lubricating bearings. And if you look at all the reasons why bearings fail, any study that's ever been done on why bearings fail, any study that I've ever looked at least, they all show that bearings fail prematurely due to lubrication related issues, whether that be over lubrication, under lubrication, lubricant contamination, which is a big one, and then just simply using incompatible lubricants or using the wrong lubricant for the wrong application. So with ultrasound, we can actually help to prevent failures due to over and under lubricated bearings. So in a sense, we can hopefully reduce a big chunk of our bearing failures just by simply using ultrasound for condition-based bearing lubrication alone. So again, we're listening for sound that is above the range of normal human hearing. And if we think about normal human hearing, every one of us on the call today, normal human hearing on the average, the upper threshold at least is around 16 to 17 kilohertz. Well, ultrasound is going to start listening at 20 kilohertz. So even at the lowest frequency setting that we can tune or set the instrument to is still above what we're able to hear as humans. So in most cases, we don't have to be too concerned about ambient or background noise because again, we're listening for sound that is above the range of normal human hearing. And then the instrument itself, through a process called heterodyning or translating, it takes the high frequency that we can't hear and then translates it into an audible that we would hear in our headset. And then it also converts that sound energy into an electrical energy that's converted to our unit of measurement for sound, which is the decibel level or the dB. So that's the primary unit of measurement that we're looking at on board the instrument. So we're going to talk about how important that dB reading is and how we use that in some of these ways that we can show energy reductions. So I've already mentioned a little bit about, tuning or adjusting the frequency. We can tune or lower the frequency all the way down to 20 kilohertz. So the concept of frequency tuning is really it's the same as the radio in your car. The radio in your car is designed to receive sound waves within a certain frequency range. Well, we do the same thing with ultrasound. We're just listening in a different frequency range, but we still have the ability to tune or set the frequency according to what the application is. So if you have an instrument already and that instrument has frequency tuning capability, you see the recommended frequency settings for the different applications. I'm showing that on the screen now. So these recommendations there's actually an ISO standard for recommended use and guidelines for airborne and structure-borne ultrasound. And that ISO standard is ISO 29821. There's a part 1 and a part 2, but you'll find these recommended frequency settings referenced in that ISO standard. So that's where they come from. So for airborne leak detection, so if we're going to do compressed air leaks, compressed gas leaks, vacuum leaks even, that frequency setting is 40 kilohertz. So you'll actually, at least on our instruments, you'll actually see what the frequency setting is. So for example, if you're using an UltraProbe 9000, a 10,000, or a 15,000, those instruments have frequency tuning capability. So you'll actually see at what frequency you have it set to. For airborne electrical inspection, that's going to be the same frequency setting of 40 kilohertz. For structure-borne mechanical, so that being, bearings, rotating equipment, pumps, gearboxes, we recommend a frequency setting of 30 kilohertz. So that's going to be a physical contact. So, we have a motor, we're going to have a motor outboard bearing, we're going to have a motor inboard bearing, and then whatever's attached to the motor. It's what we're going to be listening to with ultrasound. And then steam trap and valve testing, that recommended frequency setting is 25 kilohertz. So just wanted to give you those for reference. Now, if you have an instrument that is not on a fixed frequency setting, and even we have a couple of those, typically those instruments are going to be centered around a frequency setting of 38 kilohertz, which is kind of an optimal frequency for both airborne and contact applications. So again, I tend to call those instruments more kind of entry level or troubleshooting type instruments. So typically where we see those instruments being used is going to be with maybe if you're in a plant where you're doing operator care or operator based maintenance type inspections. Again, those are very user friendly instruments that anybody can pick those up, and they're pretty much just pull the trigger or turn it on, and it's going to be listening. So there's really the only thing that you can really adjust on it would be probably a sensitivity, which is kind of like a gain. So again, it just depends on what instrument you have, who's going to be using it, and then what kind of data you hope to get out of it. But if you have an instrument that's on a fixed frequency setting, those tend to be centered at around 38 kilohertz. Just for your knowledge. So we think about the utility of ultrasound. Since we're only listening for high frequency sound is very low energy. So that means that it's not going to travel very far from its source. So we're easily able to pinpoint and locate the source of the sound, whether that be an air leak in a large compressor room, or whether that be a machine that has several bearings within pretty close proximity of each other. Whichever one we make contact with, the one that has the highest decibel level reading, more than likely that's going to be our problem. So we can use ultrasound in noisy environments. So we've already kind of talked about that and how it relates to normal human hearing. Now, there are sources of competing ultrasounds. So if we're in an area that we are scanning for compressed air leaks, and we have someone in the background that's using air to, say, sweep the floor, or to clean a part, or to blow off their workstation, then of course that creates turbulence, and that's what we hear with a compressed air leak. But we're going to know, okay, that's supposed to be there, as opposed to if we're scanning an air hose and we come across the quick disconnect fitting and we hear just a constant rushing sound. Obviously that's a leak, and that's not supposed to be there. So having a knowledge of the equipment that you're going to go out to inspect, having a knowledge of exactly what's taking place within the area, that's certainly going to be beneficial to you as you go out to do these inspections. Number three here, allows for an early warning of failure. If we are listening to a bearing and we are trending the decibel level over time, because we're just listening for slight changes in dB or noise, that trending the decibel level becomes a really good leading indicator of a potential problem. And we pretty well know what that problem is if we know the increase in dB either above a baseline dB reading for that bearing, or an increase above the previous dB reading. We can pretty well know if that bearing is just in need of lubrication, or if that bearing is now in a failure mode that is beyond a lack of lubrication. So that's why we see a lot of people kind of using ultrasound as kind of the first line of defense, just because it's quick and easy to collect the data. And again, if we're trending the decibel level, that decibel level becomes a really good leading indicator of a potential problem. So once it reaches a certain level, we can either then record the sound file with ultrasound and look at the FFT or the time waveform, or we can come in with a complementary technology like vibration analysis, to where we can do a more diagnostic test or inspection. So it'd be a case to where ultrasound says, hey, there's a problem. Vibration comes in and says, yeah, here's exactly what the problem is. And that kind of leads into number four in talking about how complementary ultrasound is to other technologies. It's very complementary to vibration analysis on the mechanical side of things. And then it's very complementary to infrared thermography on the electrical side of things. Either way, we're trying to gather as much information as we can on an asset to make a good diagnosis on exactly what the problem is. We never recommend to anyone that they rely solely on one technology, because there's things that vibration analysis can do that ultrasound could never do. And the same with infrared. There's things that infrared will do that ultrasound could not do. But relying on one technology alone, you run the risk of not finding failure modes that one technology will not detect. So again, in either case, you want to make use of a multi-technology approach. So way number one that we can help to reduce energy waste using ultrasound is with compressed air leak detection. And this is still by far the most widely used application for airborne ultrasound. It's the easiest application, And it's the application where first time out of the box, you have the potential to more than pay for the cost of the tool. Now, obviously, you have to repair those compressed air leaks to realize the savings and the gain back on the demand, on this the CFM on the compressed air system. But it's super easy to find air leaks with ultrasound. And then once you go out and make those repairs, that's where you really start to gain back the savings. That's where you'll really start to see your compressors, the amperage draw on your compressors is going to be lower. You're going to gain back CFM on your system, and your compressed air system is going to become more efficient once we go out and locate and then repair compressed air leaks. Now, compressed air experts, and I've heard this from, you name any compressor company, and I've heard this same number, but compressed air experts will tell you that as much as 30% of the compressed air generated is lost to leaks. So we can pretty well know that at a minimum, we're going to gain back at least 30% of our capacity on our compressed air system. And then for what it takes to produce it and what you get out of it, a lot of times compressed air can be considered the most expensive utility in a typical plant or factory. Because if you look here, between 7 to 8 horsepower of electrical power is needed to produce just 1 horsepower of compressed air power. So you see kind of how expensive compressed air is. So our requirements for compressed air leak detection using ultrasound, the minimum PSI needed for ultrasonic leak testing is 5 PSI. So that's kind of what the spec on our airborne scanning modules are rated. They're rated to find leaks in the 5 PSI range. So as long as we're at 5 PSI and above, we can certainly do ultrasonic leak testing, using ultrasound. We utilize what we call a gross to fine approach. So I talked a little bit earlier about the sensitivity and how when we increase that sensitivity and how it's a gain. So when I increase the sensitivity, I'm increasing the amount of power going down into those piezoelectric crystals inside of the scanning module. So the higher the sensitivity, the more broad the field of view. So if I'm scanning an area that I want to check for air leaks, I can stand back several feet away and I scan that area, kind of left to right, up and down. And if I hear the sound of a leak, then as I move in closer to where that leak is, I'm lowering the sensitivity. So in a sense, we're starting to narrow our field of view. So once we've lowered that, then it makes it a lot easier for us to pinpoint exactly where that leak is coming from. Now, in the report that I'm going to show you, when the research was done for this about 20 years ago, we did a study with the TVA, the Tennessee Valley Authority, here in the U.S., and they had set up a test where we had known leak sizes, and then at different pressures, and we measured the decibel level at that leak size and at that pressure. And we were able to come up with a formula on how we can calculate and quantify how much those air leaks are costing us, both dollar wise and then in a CFM loss. But through that research, it was found that the approximate distance away from the leak of where we want to take that decibel level reading is approximately 15 inches away from the leak. So once we've identified exactly where that leak is, then we just simply back away approximately 15 inches and we're going to note the decibel level reading of that leak from that distance. If you take that decibel level reading too close to the leak, then it tends to overestimate how much that leak is costing. So that formula, it's based off of the decibel level. So again, that leak is making noise. So we measure the decibel level, and then it's based off of the pressure and then the cost per kilowatt hour of electricity. So how much it's costing us to generate 1,000 cubic feet of compressed air. And we actually have a leak survey app that will do all that for you. The only thing that you need is an ultrasonic device to locate the leaks. And so the leak survey app, we can enter all that information. We enter the decibel level. We can type in a description of where that leak is, the type of gas. So we have it set up not only for air, but also argon, helium, hydrogen, and other. So if your other is nitrogen, then you just simply rename other and call it nitrogen. And then any of those specialty gases, you would just enter in your cost per 1,000 cubic feet of that gas. So, and we can also incorporate photos. So we can take a photo of exactly where that leak is. So once we're ready to generate that report, we do that right here on the app. And that report is then going to be attached to an email, and we can then email that to ourselves or email that to a colleague. And this is kind of what the first sheet comes up as. So it's going to come up here with the cost tab. So if you notice here, we have the location and we have equals. So here in the US, we have gathered the information from the Department of Energy on a state by state basis for the greenhouse gas emissions. So you would just specify what state you're in, and that will give you that information as well. Your electricity costs, that's going to be your cost per kilowatt hour of electricity. And then here is your cost per 1,000 cubic feet of compressed air. And then you also have the option over here for your operational times. So we're going to assume that the air is running 24/7. But in your plant or facility, if you know the air is going to be shut off, or if you know you're going to be, shut down for holidays or a certain number of days per year, then you can adjust the hours of operation here. But it's going to default to an annual basis. So if we look at this survey here, and this is one that I actually did in a facility fairly close to where I live here in South Carolina, and in about an hour's time, we found a total of 13 air leaks. So you see over here, record number 1 all the way to 13. They were all compressed air. Here was the pressure at the leak. They were all 75 psi except for one there at 100. There's the decibel level reading, but at 10 cents a kilowatt hour, those compressed air leaks were costing this facility almost $6,800 per year. And that was just in about an hour's time, and just kind of, looking for some leaks as we were doing a training class, basically. Um, and so you can see how that is reported here in the total cost avoidance here. The total was almost $6,800 per year. And then you see the individual cost for each leak there, and then the CFM loss there. So that's the compressed air leak detection report. So number 2 is going to be compressed gas leak detection. So if you're in a facility where you are using some of the specialty gases like argon, you see here, argon might cost as much as $23 per 1,000 cubic feet. Helium is a super expensive gas, and at one time there was a helium shortage. I'm not sure if that's still in effect or not, but you can see helium might cost as much as $100 per 1,000 cubic feet. Hydrogen also very expensive, as well as some safety issues related to those types of gases. So if you're in facilities where you're using some of these specialty gases, one leak could more than pay for the cost of an ultrasonic tool that would be used to go find those leaks. And then, like I mentioned, a lot of times with these specialty gases, we have safety reasons, we have environmental reasons why we need to look for leaks. But just like with compressed air, it's going to be based off of the decibel level, the pressure, but then again, the cost of that gas. So a dollar amount per 1,000 cubic feet. So going back to our leak survey app, as you noticed here, we also have it set up for some of these other gases. So you would just enter in your cost per 1,000 cubic feet, so how much you're paying for that gas. And again, you have the same operational times there that can be adjusted. But again, the default is going to be, it's going to be on an annual or a per year basis. So here is just a sample report that I was at a particular facility that were using nitrogen and helium, and these were just 5 of the leaks that we documented. So we found a total of 3 nitrogen leaks; those were at 75 psi, and we found a total of 2 helium leaks; those were at 50 psi. Here's the decibel level reading. But those 5 leaks alone were costing this facility a little over $27,000 per year. So again, very expensive, and you can see, this the most expensive one was this nitrogen leak at 75 psi, 38 dB, and it was costing them, based off of how much they were paying, a little over $7,600 per year. Now, I will say that either one of these reports, either the compressed air leak report or the compressed gas leak report, um, these tend to err on the conservative side. So we've always said that the savings is going to be within 20% of what is reported here. So we've kind of just always been under the belief that it's better to come in a little bit low and the savings be more than to come in high and the savings actually be a little less. So again, we've tended to kind of err on the conservative side, and we've always kind of said that it's within 20% of the actual savings. Now, we've had some other documentation, and research presented at our Ultrasound World Conference, and there was one study that was done by a company out of Ohio that, again, they set up their own test, and they said it's within 8% conservative. So, but either way, it's going to be a conservative estimation, if you will, of how much these air or gas leaks are costing. But either way, it's going to be fairly close. Number three, we look at carbon footprint reduction, and we're going to go back to the report here in just a moment. But a lot of plants, a lot of facilities, they like to track this now. And if I'm going to go in to visit a plant or a facility, and if it's unfamiliar to me, if I'm not familiar with the company, of course I'm going to check out the website. And if I go to the website, a lot of times I'm going to see a tab or a comment about sustainability or energy conservation. So that kind of lets me know kind of what their mindset is before I even go visit that facility. So if we look at carbon footprint reduction, it's big time here in the U.S. as well as in other parts of the world. But if we look at electricity and industry account for 50% of the total greenhouse gas emissions in the U.S. And if we look at how that electricity is produced, 62.9% of electricity in the US comes from the burning of fossil fuels. And these were 2017 numbers. And then also, if we look at industry specifically, again, primarily comes from burning of fossil fuels for energy, as well as from certain chemical reactions necessary to produce the goods from raw materials that you all produce in your factories. So if we can show carbon footprint reduction with our initiatives, then that can go a long way in our overall energy initiative for that particular plant, or if it's a corporate wide type of initiative. So going back to our compressed air leak report, the very first one that I showed you, if we look over the last 4 columns of that report, and this kind of goes back to why we need to specify what state we're in, because based off of where we are, the DOE has their own formula for how the power is produced. So if you're in areas of the country where it may be considered to be more clean, so if you have more nuclear or if you have more hydro, as opposed to areas where maybe you have more fossil fuel related energy generation, like with coal or even natural gas, the carbon footprint is going to be a little bit higher in those areas. So again, if we look at the last 4 columns of that same sheet, the last 4 columns, that's going to be our energy or our greenhouse gas emissions information. So as we repair these leaks, we will be able to see how much we have reduced our carbon footprint emissions by, because the spreadsheet will update that for you. And you even have a report tab here at the bottom that will track your progress. So you'll even be able to see the percent air leaks repaired completed, or you'll be able to see the carbon footprint reduction compared to what the overall total was for each one of those greenhouse gases. So again, all that information we got from the Department of Energy on a state by state basis, and we've incorporated that into that leak app or that leak report. So number four, we've talked about it a little bit already, but steam traps, steam trap testing and inspection. So again, steam experts have told me that if you haven't had a steam trap survey done in your facility for at least 3 to 5 years, so if it's been 3 to 5 years since any of your steam traps have been tested, as many as 50% of your steam traps could be in a failed condition. Being either leaking by steam, or the trap not operating properly, or the steam trap is either failed open and blowing live steam across the seat of the trap 24/7. But if we look overall, over 45% of all fuel burned by US manufacturers is consumed to generate steam. And again, depending on where you are, and what kind of industry you're in. So really, especially if you're in pharmaceutical tends to be, very expensive steam, to where, it has to be very clean. It has to be treated. Typically in those areas, the fuel used to generate the steam is going to be higher. So our cost of steam is going to be increase, as opposed to if we're just using steam in, say, a paper mill, for heating or drying of the paper. But a typical facility can realize steam savings of up to 20% just by simply improving the steam system. Simple improvements could be just by simply inspecting and repairing and then maintaining steam traps. Another simple initiative to improve the efficiency of your steam system is just by simply insulating the pipes. If you drive into your plant, and again, just to give you a good visual, look at the roof line. If you see excessive steam venting to atmosphere, it's usually a good indicator that you have some failed steam traps on your system. Typically, they're going to be failed open. I have been to one plant in particular about 10 years ago, and they had a steam vent near the front entrance of the plant. And instead of excessive steam venting to atmosphere, it was actually excessive condensate venting to atmosphere. So it looked like they had a rooftop water fountain. So obviously, again, just a good visual when I'm going into a plant. I'm looking around, I'm looking at things. So if you see excessive steam venting to atmosphere, usually a good indicator that you have some failed steam traps. Another stat here from the Federal Management Program through the DOE. Again, approximately 20% of the steam leaving a central boiler plant is lost via leaking steam traps. So similar to our number with compressed air, steam experts will tell us, hey, as much as 20% of the steam leaving a central boiler is lost via the leaking steam traps. So similar to the compressed air leak app, again, we've got another easy way that we can document and then quantify any losses associated with steam traps. Now, with compressed air and compressed gas, there were only three variables: the decibel level, the pressure, and then either the cost of the cost per 1,000 cubic feet of compressed air, or a cost per kilowatt hour of electricity, or the cost of that specialty gas, so the dollar amount per 1,000 cubic feet. With steam, there's a few more variables involved, but it's all information that is readily accessible, and you probably already have it if you have a steam trap database. Is we need to know the type of trap, whether that be an inverted bucket, a thermodynamic, a disc style trap, or a floating thermostatic. We need to know the type of the trap. We need to know the orifice size, and then we need to know the inlet temperature and the outlet temperature. So the old way that we used to quantify steam loss is if we knew the orifice size, and then if we knew the pressure, the psi of steam. Now with steam, the psi is kind of equal to the temperature. So the higher the pressure, the higher the temperature. So we would go to this leak rate table. So it'd be basically a sheet of paper, and we would go down, we find our orifice size, and then come across to find our PSI steam, and then there would be a leak rate in pounds per hour across that orifice size. So then we would just plug that into our hours of operation and then our cost of steam, and that's going to give us the dollars for how much that steam trap is costing us if it's in a failed open condition. But since we know that the temperature and the pressure of steam is kind of correlated or directly correlated, if we know the inlet temperature and the outlet temperature, that's going to equate to the pressure. So that's why we need to know our temperatures. And then we're going to enter the test results. So we've tested it with ultrasound, and based off of our test, we've determined if the trap is okay, if it's operating properly. We've determined if it's leaking by steam or if that steam trap is either failed open or failed closed. Now, if you check a steam trap with temperature first and you check your inlet temperature and your outlet temperature and the temperatures are the same, it's pretty well safe to say that that trap is probably failed open, meaning that it's blowing live steam across the seat of the trap. It should be somewhat cooler on the outlet side of the trap. So anyway, we want to test with temperature first. If we have a high temperature, that lets us know that we have steam coming to the trap, and then we can proceed to test with ultrasound to make sure that trap is working properly. So we enter all that information on the app, and really, kind of this app becomes our steam trap database. And a lot of times we've seen where the biggest challenge for people when it comes to steam traps is they don't know where all the traps are. If you're in a refinery or if you're in some sort of a chemical type facility, you may have hundreds, if not thousands, of traps. And if your plant is of any age, things have been added to, things have been taken away. Lines are still there that are no longer in service. So we have to have a good database of our existing and in use steam traps. And this is going to be kind of the start. So a lot of times that can be just simply the biggest challenge getting started is knowing where all the traps are and then creating a database. But the app can certainly do that. So here is just a little survey that we did. We did a total of 5 steam traps. So you can see here was the type of trap. So we had 2 floating thermostatics, we had 2 inverted buckets, and we had 1 thermodynamic. We determined based off of the temperatures and based off of our ultrasound test that we had 2 that were leaking by, we had 2 that were failed open, and we had 1 that was okay. So our cost of steam, so similar to that cost tab that you saw on the compressed air leak report, um, you have the area here where you would enter in your cost of steam. So in this case, it was $10 per 1,000 pounds. And before I mention the total there, you see here the percentage of leak by and then percentage of failed open. So again, we're kind of erring on the conservative side, but if we have a trap that's leaking by, we're assuming that it's leaking by at 40%. If we have a trap that's failed open, we're assuming that it's only failed open or blowing by 80%. Now, you could change those numbers if you wanted to make it a little more conservative. So if you have one that's leaking by, you could even say 30% and then maybe 70%. But either way, it's going to be a conservative estimation for how much those traps are costing. So at $10 per 1,000 pounds, those 5 steam traps, the 2 that are leaking by and the 2 that are failed open at least, are costing this facility a little over $4,700 per year. And that's just 5 steam traps. And that's a very low number on the cost of steam. I've heard as high as $18 per 1,000 pounds. And again, that tends to be more in the pharmaceutical type of industries where again typically the fuel used to generate the steam is going to be a little bit higher, and then just the steam has to be cleaner, it has to be treated and maintained differently. So that's how we would quantify steam trap losses using ultrasound. And again, it's based off of the type of trap, the orifice size, the inlet temperature, the outlet temperature, and then our test result, if it's okay, if it's leaking by, or if it's failed open. Or we may have some that are failed closed, and those are going to require, I guess, more significant maintenance or repair. And then our last way that we can use ultrasound to improve energy usage in our plants and facilities is going to be through mechanical efficiency and friction. So if we, again, kind of talking about, bearing lubrication, we talk about that application and really it's friction related. But if we look at, again, some of the energy stats that are related to mechanical or motor driven equipment, again, industry uses more than 1/3 of all energy in the US. Most energy industry uses is supplied from natural gas and petroleum. But motor driven equipment accounts for 64% of the electricity consumed by US industries. So if we have motors that are more energy efficient, we can cut that by at least 12%. So if we are using ultrasound to more precisely lubricate bearings, we are improving the efficiency of that motor and of that bearing specifically. So directly related to friction, we can hopefully use ultrasound to reduce those cases of where we have friction related failure modes. And if we think about friction itself, obviously when we have increases in friction, we have increases in temperature. That's going to contribute to energy loss. That motor is using a greater amount of power to overcome. When you have expansion of the metals, due to friction, expansion and contraction, that is destructive over time, and it can cause the bearing or the sliding surface to fit tighter, or in some cases, looser. But through the use of ultrasound, we can prevent over and under lubricated bearings, and those are sources of friction directly related, to motor-driven equipment. But either way, friction is going to be the source of the high frequency sound. So when we have a bearing that needs grease, there's going to be an increase in friction. When you have a bearing that is over lubricated, there's going to be an increase in friction. So the picture that you're seeing here, this motor, the bearings on this motor, these bearings were lubricated on timed based intervals. So they had specific PMs that said to apply a certain number of pumps of grease to these bearings. And the person that did the lubricating, they didn't intentionally do anything wrong. They were basing it solely off of what that lubrication procedure told them to do. But obviously, it was too much too often. So when you see cases like this, obviously, we can prevent this using ultrasound. And then if you look at the bearings here, this motor overheated so much that we've started to see spalling and discoloration, which is very typical when you look at friction related failure modes on bearings. So again, just like with turbulence, with air leaks, with ionization, and being the source of electrical faults, like our corona tracking and arcing, friction is the source of the ultrasound when it comes to bearing and bearing lubrication specifically. So again, if the bearing needs grease, there's going to be an increase in dB. So what we want to see happening is if we're using ultrasound to listen and watch the decibel level as we're applying grease, we want to see the decibel level falling as grease is applied. So again, once grease enters that bearing housing, there's less friction, therefore less noise. Now, if the bearing is already sufficiently lubricated and doesn't need any grease, then usually the response is fairly quick. Usually just after a couple of pumps of grease, the decibel level will start to increase. So if we're ever applying grease to a bearing and the decibel level starts to increase, it's an indicator to let us know that we need to stop applying grease because we've now reached the threshold where we've started to apply too much grease. So, and you kind of see that here on the top image that you're seeing here. These were sound files of a bearing in the process of being lubricated. So we recorded the sound file of the bearing as we were applying grease, and we played these back and we looked at it in the time waveform. So what you're seeing here is starting over on the far left, you see before lubrication, and then we added grease and we had a nice gradual fall back down to a more normal level, and then we stopped greasing. So again, on the left is before lubrication, on the right is after lubrication. The image on the bottom, it's a little bit longer of a sound file, so we're at 48 seconds here as opposed to 13 seconds on the top one. But it shows what happens when we have applied too much grease to a bearing. So again, starting on the left, you see a huge increase in amplitude or an increase in noise. But then we applied grease and we had a really nice fall back down to a more normal level. And that's really where they should have stopped. But they continued to apply grease, and you can just about count every pump of grease thereafter how the amplitude starts to increase. So again, when we over lubricate a bearing, we're increasing both pressure and friction inside that bearing housing, and therefore more noise. So just wrapping up here, we think about ways that we can incorporate energy management or energy conservation into our reliability program. Ultrasound, hopefully you've seen, can play a major role in helping to reduce energy inefficiencies in a typical plant or facility, especially with compressed air leak detection. It's the easiest thing you can do, and it's the application where you're going to have the quickest return on investment. And a lot of times people are quick to either, rent a compressor to keep up with demand, or, we look at expensive capital projects to install new compressors or backup compressor, when really, if we start with leaks, find the leaks, and then repair those leaks, that can go a long way in helping to improve the efficiency of our compressed air system. And a lot of times we don't need that rental compressor, or we don't need to make that big capital investment to install new compressors. Any of these energy applications, though, are going to be some of the easiest applications that you can use and deploy for ultrasound. And, if we look at, again, improving reliability in our plants and facilities, reliable assets help to make reliable plants. And reliable plants tend to be more likely to be energy efficient plants. So some of these initiatives can also be directly related to improving reliability. But really, it's about making more with less, and it's being efficient with our resources. And it really becomes a competitive advantage. If you're in a facility and you're making a product and you can make that product more efficiently and more reliably than your competitor, then that certainly is a competitive advantage. And I would also encourage you to track KPIs directly related to energy usage, especially if you're getting ready to start some of these initiatives. Again, track those energy KPIs before, during, and then after to track your progress. And it's just another thing that you can do, another way to report your findings, and another way to just showcase the progress and the success that you have made and creative through that initiative. But I would encourage you just to do something. Again, if you don't do anything else, a great place to start and a great thing to do is to form that energy team and walk that plant, walk that facility uh, with energy in mind. Think about ways that you can do the same thing, but do it more efficiently and do it by using, less energy, just so it's not as wasteful. So with that, Heather, we can open it up for any questions that may have came in.
Hello. Yes.
Yeah.
Wonderful. Thank you so much, Adrian. That was really thoughtful, deep dive into and great examples in there with all of your main points. So really enjoyed that. Thank you so much.
Appreciate it. Thank you.
Yeah. We had a comment come in from Greg that is just a comment and a recommendation, but recommending you as a seasoned professional and their go-to guy for training people in their plant. So that's pretty cool, I thought.
Oh, well, thank you, Greg. I appreciate that.
We had a couple of quick questions come in. One here from Ahmed says, Adrian, if the quality of grease has deteriorated, then can you get an indication?
Yeah, that's a really good question. And usually by the time the grease has deteriorated, that bearing is going to be in a lack of lubrication condition, I would say. So if it starts to separate, or if if the oils, start to break down that are in that grease, then I would say that definitely there you would see an increase in decibel level. Now the decibel level may not drop. So if we were to apply fresh grease to that bearing, we may not see drastic drops in the decibel level as we apply grease to that bearing. But I would say certainly we would see some sort of drop or decrease in dB once we've added fresh grease to that bearing. But we really wouldn't know unless we actually physically take the bearing out to see if they've had that separation, that lubricant breakdown, or the deterioration in that lubricant.
Awesome. I hope that helps answer your question. Another question here, we might have touched on this, I think, throughout the presentation, but is ultrasound technology a solution for all types of plant, or does it benefit a certain type of industry more than any others?
Yeah, no, that's a great question. We tend to be more in the, I would say, mid-level manufacturing. So we have typically done very well in say food and beverage types of industries, or where it's really just about run, making product. So we're good fits in those types of environments because hopefully just in this presentation alone you've seen how versatile ultrasound is. So if you're in a plant or a facility where you're not doing very much, condition-based monitoring, or CBM, condition-based maintenance, ultrasound is a really good fit because not only can we use the same tool for air leaks, we can use that same tool for bearings. We can use the same tool for steam traps. So in plants or environments like that, ultrasound tends to be kind of the standalone maintenance tool, which is okay because those types of plants typically aren't doing in-house vibration analysis. Typically they're contracting things out, say an annual infrared scan as an example. So we have typically been very good fits in, again, what I would call, mid-level type manufacturing, but, we're in all sorts of plants and facilities, anything from offshore oil rigs to, cruise ships to, potato chip factories to, high-rise buildings. So we're really not heavy in one sector or another, but where we typically have seen a lot of success is going to be in that mid-level type manufacturing and plants to where they're doing very little in-house CBM type work.
Awesome. Those are the only two questions I'm seeing. So I think we're just about at the end of our time here. Thank you, Adrian, once again for a wonderful presentation. Thank you so much, everyone, for joining us this afternoon, this evening, again, wherever you are in the world. The recording from today's session, as well as the slides that you see here, will be available in the Slack community starting tomorrow. So be sure to join once again if you are not already a member. That's all from me. Have a great rest of your afternoon, your evening, and I'll see you next time.
Awesome. Thanks, everyone.
Thanks, Adrian. Bye-bye.